So we've seen how differentiation works in polar coordinates. Now it's time to work on integration, right? So integration in polar coordinates is a bit different. So we start with area, which of course is a metaphor for definite integration. And we learned that in Calc 1. Let me remind everybody. So in Calc 1, you started off all problems, if you remember, with pictures that looked like this. And you'd be finding the area under the whole thing. And for both of these, whether it's the area of a sector on a circle or the area underneath this particular weird trapezoid that I made, you can use geometry. If you remember back to your Calc 1, that's where integration always kind of begins. Like, let's think about the area under kind of a weird curve that we could figure out with geometry using like rectangles and triangles. And then we go from there to what if it's not something that we can figure out with geometry? What if it's a weird curve? Now remember, this would be a polar region swept from theta equals A to theta equals B. In Calc 1, what that would mean was instead of having that weird geometry shape, you'd have some weird curve, and you'd want to be finding the area under that curve from x equals A to x equals B. Okay? So in Calc 1, this is how it would look. Right? But in a polar region, what you're trying to find is the area bounded by your polar function, which could be this weird wavy curve thing, from theta equals A to theta equals B. Now, what we can do is what we did in Calc 1. So in Calc 1, we would take that region that we had, and we would divide it up into rectangles, if you remember Riemann sums. So we'd take the rectangles and we would find the area of the rectangles. We do, left Riemann sum, right Riemann sum, etc. Right? Well, we can do the same thing with a polar curve. But instead of rectangles, what they'll be is areas of a sector. So you it's sort of like a midpoint they're doing here. So you touch the curve there and then you build, and that little section right there is like a piece of pie. It's called it's an area, it's a sector. It's the same thing as what you're doing up here. So you have one little sector right here, right? And then you have another little sector next to it, right here, right? So you grab the curve in kind of the middle there, and then you have another little sector next to it, and so on. So what they are is, imagine a circle that would go all the way around the pole as the center, and this little piece is a section of that circle, which is called a sector. And what you do is you let n go to infinity. So you say, okay, I'm going to let the number of sectors that I'm going to fit into this be, the number of sectors go to infinity. So you're going to get smaller and smaller sectors, just like we did with Riemann sums here. Actually, let me remind you of this for a Riemann sum. So if we let the number of rectangles, n, go to infinity, you can see that the rectangles are doing a better and better job of approximating the area under that curve, and each one of those rectangles is taking up a smaller and smaller section of the graph, right? The same thing is true for the polar graphs. So if we let n go to infinity, then the sectors, right, because each of these is a sector, right? The sectors will get very narrow, and each sector has a smaller and smaller angle. So there's an angle down at the bottom. Right, the sectors themselves will actually get very small, just like it does if you increase n here, right? So right, but if we sum them up, right, if we take the sum of those sectors, well, I guess I should say the sum of the infinitely many sectors, right, will be equal to the area within the curve, the polar curve, from theta equals A to theta equals B. Right? That's what we're doing. So it's the equivalent of Riemann sums, which were rectangles, letting n go to infinity, except they're little pieces of a circle, right? And then you let n go to infinity, and so they'll each be tinier and tinier and tinier pieces of that circle, and it will fill out this curve, just like these rectangles fill out that curve. Calculus, it's a beautiful thing. All right, so that is the idea behind this lovely formula right here. So the area in polar coordinates. So if you have a continuous and non-negative function f on the interval from alpha, which is less than or equal to theta, which is less than or equal to beta. So that's alpha. It's a Greek letter. That's beta, another Greek letter. Okay, so, and 0 is less than beta minus alpha, which is less than 2 pi. So you don't want to go around more than once, right? So in other words, beta is the larger of the two angles, right? And then they're between 0 and 2 pi between them. Then the area of the region is bounded by the graph of r equals f of theta between the radial lines theta equals alpha and theta equals beta is given by this formula. So this formula is the formula for area in a polar curve. Now, what's going on here? Well, we're going from theta equals alpha to theta equals beta, but why is it 1/2 f of theta squared? It's 1/2 r squared. And the reason for that is it's the formula for the area of a sector. See? So the area of a sector is 1/2 theta r squared. The area of the entire circle, of course, is 1/2 r squared. But theta is this angle right here, right? So 1/2 theta r squared is how we're building these, because these are each little sectors, right? So a sector, each sector has a 1/2 theta r squared formula, right, for each one. And so we're using those little areas here. So it's 1/2 r squared, and the theta part is taken care of from the alpha to the beta integral sign, because of course we're integrating with respect to theta. So let's apply this to this problem. So we want to sketch and find the area of one petal of the rose curve given by r equals, 3 cosine of 3 theta. That got moved there a little bit. So that's my f of theta right there. The 3 theta was kind of nudged over here. Assume r is measured in centimeters. Find the area of the entire rose curve as well. Okay, so a couple of things. I need to know the period of this curve because I need to know what I'm going for. So I've got the graph here in Desmos. All right, so technically at negative pi over 6, the picture starts getting drawn. So negative pi over 6 is right here. And then pi over 6 is right there. So I'm ending it at pi over 6. And then it loop-de-loops around and it circles back, right? So if I just want the one flower, there's a couple ways I can do this, right? So I can figure out just the area from, so instead of going negative pi over 6, I can start at 0. I'll let you see what that looks like. So if I start at 0, right here, notice that bit of the curve is already drawn because of the way I have it, right? So 0 to pi over 6 will get me that piece of the flower. So let me shade that. So if I go from 0 to pi over 6, that would do this piece, right? And I also notice, by the way, when I'm looking at it, that the period is pi. Right, I could tell that when I was looking at it. So the period is pi, and let's think about this. 3 cosine of 3 theta is equal to 0 when the cosine of 3 theta is equal to 0. I'm proving to you that the pi over 6 is what's happening here. So that cosine is equal to 0, right? When that angle, 3 theta, is equal to pi over 2, 3 pi over 2, 5 pi over 2, etc. So that would mean theta, my angle, is pi over 6 because you multiply both sides by 1/3. right? So that'd be pi over 6, 3 pi over 6, which is pi over 2, and then 5 pi over 6, right? So I'm right. It's not just a guess from Desmos. It really is from, it really happens at pi over 6 that it comes back into the pole. So I'm really finding the pole values right here. So my pole values, where the angles that it comes back and touches the pole, is pi over 6, 3 pi over 6, aka pi over 2, and 5 pi over 6. So if I want the area of petal number 1, what I'm going to do is I'm going to find the area of half the petal, right? Because I can go from 0 to pi over 6, right, which is my highlighted piece. The area of half petal is 0 pi over 6. I want f of theta, which is 3 cosine of 3 theta squared d theta. And then there's a half in front. But think about what I'm doing, right? I actually only have from 0 to pi over 6. From 0 to pi over 6 only gets me this piece. If I want the whole petal, well, it's symmetric, right? So I can just multiply the whole thing by 2. If I multiply the whole thing by 2, that'll get me the whole petal. So I took the integral for half of the petal, and then I multiplied by 2. Nice, huh? And I'll call this, I don't know, area, right? So A. Okay, so that area is equal to the integral of 0 to pi over 6. I don't have to worry about these because they cancel, right? 2 times a half. So 0 to pi over 6. And then that's 9 cosine squared of 3 theta, right? Because 3 times squared is 9. And that would be the 9. All right, now I have to integrate this. Right, there's a 9 out in front, obviously, but I need a little space here. So u is 3 theta. Du is 3 d theta. Oh, so I could actually change that. So I could do this either as 1/3 du equals d theta, or I could manipulate the 9, but it'll work out either way. And let's think about our angles. So I want theta equals 0, so that would mean u is 0. No problem. If theta equals pi over 6, u is 3 times pi over 6, which is pi over 2. Okay, so then I can use the substitution. So I can say, okay, I have a 9, I have a 1/3. Right, those will obviously cancel a little bit in a minute. I'm going to go from 0 to pi over 2 now, and then cosine squared of u du. That's a formula on our big integral table. There, looking at the giant integral table, I can see it's number 52. So number 52, let's see here. This will be 3, because 9 times 1/3 is 3. And then this will be 1/2. And then u minus, or u plus, sorry, u plus cosine, sine u cosine u. So it's right there. U plus sine u cosine u. And of course I'm taking that from, sorry, I had to pull up my cheat sheet. I'm taking that from u is equal to 0 to u is equal to pi over 2 because I'm integrating with respect to u. Okay, so that would be 3/2 times, and then I'm going to put pi over 2 into this. So pi over 2 plus 0, actually, because the sine of pi over 2 is 1, but the cosine of pi over 2 is 0. So that's 0 minus 0 plus 0. So that didn't work out. The whole thing is 3 pi over 4. And it would be centimeters squared, which is the area of one whole petal. With these flower curves, you really want to trim it down to the smallest symmetric piece that you can find easily, and then just multiply it by however much you need. Speaking of which, if I want the area inside all the petals, right? You don't just integrate from 0 to 2 pi. It actually won't work. The integral from 0 to 2 pi, or the 0 to pi for that matter, would be 0. Like, it's not going to work. But what you can say is the area of the whole flower, well, there were 3 petals, right? Is 3 times the area of a petal, right? Which is 3 times 3 pi over 4, which would be 9 pi over 4 centimeters squared. You do not integrate. This is a big note. You do not just try to integrate from 0 to pi. It won't work. 0 to pi would actually give you 0 as an answer, right? What you do is use the smallest symmetric piece that works easily. Usually a half petal, or sometimes a whole petal. And then you multiply.